The title of today's lesson is Rational Functions. By the end of this lesson, you'll be able to identify characteristics of the rational functions as well as being able to graph the rational function. So let's get the definition of what a rational function is. It's a function that can be expressed as the ratio of two polynomials. For example, if I have f of x is equal to, let's say, p of x over q of x, where both p of x and q of x are polynomial functions. Also, q of x cannot be 0. If q of x was equal to 0, then we'd have dividing by 0, and we can't have that. So here's two examples of what a polynomial function can look like. F of x equals 3x plus 2. Notice this numerator is a polynomial. Over 4x squared minus 5x plus 1. The denominator is also a polynomial. When you take the ratio of these two polynomials, the entire function then becomes a rational function. Rational, again, coming from the word ratio. Similarly, on g of x, the numerator is a polynomial, the denominator is a polynomial. Our goal today is to be able to identify the characteristics of these polynomials and also be able to graph them. So first, let's look at the domain. We've actually already talked about the domain of a rational function before, so this part might be a little bit of a review, but it's important that you cover it right before we graph, so we will be doing it again. Domain. The domain of a rational function is all real numbers except those for which the value of the denominator is equal to 0. We said earlier that q of x, the whole function, couldn't be 0, but in the polynomial in the denominator, there may be some places that when you plug in an x value or a domain value, that you'll get out a 0. And in those cases, the function won't be defined, and so we have to exclude that from the domain. To determine the domain of a rational function, I want you to set the denominator of the rational function equal to 0 and solve for x. Any real number obtained will need to be excluded from your domain. So let's go ahead and practice this. For the function f of x equals 6 minus x over 2x plus 1, I'm looking for the domain, and I know the domain is going to be all real numbers except if x makes the denominator 0. So what I'm going to do is I'm going to set that denominator equal to 0. Or actually, you might even consider thinking about it as not equal to 0. I can have all the values as long as it's not equal to 0. And then when I solve, I'm getting 2x equals negative 1. Divide both sides by 2, and I get x is equal to negative 1/2. Or x can't be negative 1/2. X can be anything else it wants to be. Anything except negative 1/2. And if you think about that on a number line, we have no value at negative 1/2, but every single other value you're allowed to have. So my domain in interval notation is negative infinity, comma negative 1/2, union negative 1/2 to infinity. All numbers except negative 1/2. Looking at the next problem, g of x is equal to x plus 2 over x squared minus 9 is a rational function because we have a polynomial divided by a polynomial. Our domain is going to be all real numbers except if we have a domain value that makes the denominator 0. So I'm going to explore that case. Where does x squared minus 9 equal 0? Or really where I want all the values where it is not equal to 0. X cannot be negative 3, and x cannot be 3. What can x be? Everything else. So at negative 3 and at 3, I have holes in my domain. So my domain given in interval notation, is negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. For our last rational function, I have h of x equals x plus 2 over x squared plus 9. My domain is going to be all real numbers, except if there's a value that makes the denominator 0. So I'm going to set the denominator equal to 0, or really not equal to 0, because I can have everything else except that. This doesn't factor quite as nicely as the last one did, so I'm going to move the 9 over. Take the square root of both sides, and I have x is equal to plus or minus 3i. Well, I can't really exclude a plus or minus 3i from the real numbers because plus or minus 3i is not real. Notice it says any real numbers obtained will need to be excluded. So what values am I allowed to have? Well, all real numbers. I can't very well exclude imaginary numbers from my real number line, so my domain is all real numbers, negative infinity to positive infinity. Which, if you think about it, kind of makes sense. If I plug any x value into the denominator, if I square it, I get something 0 or positive. And if I add 9 to something 0 or positive, I can never get back to 0. I'm taking something non-negative, I'm adding something to it, I'm never going to get 0 in the denominator. Therefore, my domain is all real numbers. The next thing we need to look at after finding the domain of a rational function is find out what happens at those excluded values. Notice that the excluded values of the domain, the function is not defined. So if the function is not defined, then the graph cannot be continuous at these excluded domain values. So something weird happens at these points. So my first function, something weird has to happen at negative 1/2 because it can't go right through the graph of the rational function can't go through negative 1/2. It does not define there. For my second function, I can't be defined at negative 3 and I'm not defined at 3. So because my graph can't be defined at these two values, something weird has to happen. And there's one of two things that can happen. At the excluded domain values, the graph may have a hole, making it non-continuous, or it may have a vertical asymptote. So those are the two things that we're going to look at. What is a hole and what is a vertical asymptote? We'll be using lots of asymptotes, so let's just give you a quick definition of what an asymptote is. An asymptote is a line or curve that our graph gets close to. And we're going to use, in math terms, we like to say approaches. But approaches just means my graph is going to get really, 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 really close to it, but usually does not cross or touch. So the asymptote gets really, really, really close to it, but it doesn't ever touch it. Let's give you a visual example of that real quick. We'll be talking about holes and asymptotes, but if you just look at these two pictures that I've given you over here, notice that there's a line right here. That line is not part of the graph, it's an asymptote. Notice that the graph gets really, really, really close to the line, but it won't ever touch it. Similarly, we have a horizontal line right here, and it does the same thing. Your graphs are getting really, really, really close to it, but it won't ever cross or touch. And actually it says usually doesn't cross or touch, because there is one counterexample of them. So I'm going to go ahead and erase this because we'll be talking a little bit about holes and asymptotes, but I really just wanted to talk to you about what an asymptote was, what it looked like, and how it behaves. So at these excluded values from the domain, you're either going to have a hole or a vertical asymptote. You'll have a hole if a factor from the numerator and a factor from the denominator divides out. Some teachers say cancel out, same thing. Then the graph will have a hole at that excluded domain value. How to find those? We're going to factor and reduce the expression. If a factor divides out, then set that factor equal to 0 and solve for x. plug in the x value to the reduced function to find the corresponding value for the point of the hole. Let's take a look at this example. F of x equals x minus 3 times x minus 1 over x plus 1 times x minus 1. Notice that there are two excluded domain values for this problem. I cannot be -1 and I cannot be 1. Now I know I probably should write that at interval notation. I just wanted you to understand that these are the two values, -1 and 1, are going to be problem areas. Those two numbers will either be a hole or a vertical asymptote at those x values. So let's take a look at the function. Notice we have an x minus 1 factor and an x minus 1 factor in the numerator and the denominator. They are going to divide out. Because they divided out, that's going to create a hole. And I set the factor equal to 0 to find out where the hole is. So we have a hole at x equals 1. So I have a hole at 1 comma some value. How am I going to figure out what that other value is? Well, step 2 says plug in that x value to the reduced function. Notice that my reduced function is f of x is equal to x minus 3 over x plus 1. The remaining two factors after I divided out the common factor. So when I find the value of 1 at the reduced function, I have 1 minus 3 over 1 plus 1, or negative 2 over 2. I'm getting a hole at -1 comma -1. Notice in my picture, I had a hole at 1 comma -1. The graph is continuous all the way up right until that point, and then it kind of jumps right over and keeps being continuous all the way towards the asymptote. So my hole is at 1 comma -1. If I factor divides out, you get a hole in your graph. Although the other excluded domain value we haven't talked about yet. At x equals 1, we had a hole. So what happens at the other excluded domain value? Well, in that case, we have a vertical asymptote. A vertical asymptote is a vertical line where the graph approaches. No, this is just an example of a vertical asymptote here. We usually use a dotted line to denote an asymptote, and your lines get really, really, really close to it, but never ever crosses or touches. A vertical asymptote is a vertical line where the graph approaches, but never crosses or touches. In the definition of an asymptote, I said usually doesn't cross or touch. Well, vertical asymptotes will never, ever, ever be crossed or touched. After you reduce the expression, I want you to set your remaining denominator equal to 0 and solve. This will be your vertical asymptote. Notice that there could be several vertical asymptotes, but the graph will never, ever, ever cross the vertical asymptote. I really want to make sure you understand that. Let's finish the problem we started up here. I know I have a reduced function at x minus 3 over x plus 1. We talked about already having a hole at 1 comma -1. But notice I have this reduced function, and I'm going to use that reduced function to find the vertical asymptote. I'm going to set the remaining factor in the denominator equal to 0 and solve. X equals -1 is going to be my vertical asymptote. And if you look at the graph that we had of this function here, notice x equals -1 was our vertical asymptote. So the domain will tell you the excluded values. Those excluded values will either be a hole or a vertical asymptote. Notice that the graph is continuous all the way up until the vertical asymptote, and then it has to jump because it can't be equal to the value at x equals -1. And then it's continuous until we reach the hole, and then it has to jump, and then it's continuous on for the rest of the graph. But there is no value at the hole, and there is no value at the vertical asymptote because they are excluded domain values.